All right, so this time what we want to do is look at what's the reality of operating a cycle that is the scheme of the ideal Brayton cycle, but is no longer internally reversible. So I'm going to incorporate process efficiencies. We've done this before. We did this in the Rankine cycle. No brainer. For a compressor, it operates much like a pump. The ideal is adiabatic or isentropic. And the power of a pump in reality always requires more power than what the ideal would indicate. So Ws over Wa will be a ratio less than 1, which will be the definition of the process efficiency for the compressor. A turbine produces less power than what you would ideally predict. So the actual amount of work is large or smaller than the ideal amount of work. And so Wa over Ws is a number less than 1. That's our process efficiency for the turbine. So let's now use those by applying them to the example that we had just looked at. So these were the values that I'd gotten before. Pressures were all given. T1 was given and T3 was given. And based on given temperature, I could look up everything else for state 1 and state 3. I then used pressure ratios to determine PR at states 2 and 4, and then found all the rest of the data for states 2 and 4. But that assumed isentropic, ideal, reversible compressor and turbine. Let's say they're not. Okay? So 65% efficient compressor, 75% efficient turbine. In that case, let me this time go through and calculate the amount of work for each component. So my compressor, it's the enthalpy at the inlet minus the exit. So the ideal amount is going to be H at state 1 minus H at state 2. Tells me that the ideal compressor will require 75.5 BTUs per pound mass. The actual compressor, I'm going to take this and divide by the compressor efficiency, 65%. So negative 75.5 divided by 0.65 says that the actual compressor is going to require 116.2 BTUs per pound mass. Now that means that the actual exit enthalpy can be calculated using this same definition for work, except I'm now going to put the actual exit paired with the actual amount of work. So if I solve for the actual exit enthalpy, it's H1 minus the actual work is 228.4 BTUs per pound mass. Now it isn't necessary to know this, but it's kind of interesting to see since it's an ideal gas. 228.4 BTUs per pound mass corresponds to a temperature of about 1,000. So not only am I having different numbers for my enthalpies, but we have a very distinct difference in what's going to happen to my temperatures inside the cycle. Now, so this is going to be 1,017 degrees R. That's kind of interesting because what that tells me is I'm going to have this stuff preheated more than I thought I was, right? So maybe this is good. Okay, so 1017, and I can get other data also. If I needed to calculate entropy generation from the cycle or something like that, I would be able to do it using this information. Now the turbine. Ideally, it's H3 minus H4 using these isentropic assumptions. So 645.7 minus 417.6, it produces 171.3 BTUs per pound mass ideally. Oh, wait a minute, no, 228.4, excuse me, read the wrong number off my calcs. Now, that's the ideal. The reality, I'm going to multiply by my 75%. I want a lower number. Well, I don't want a lower number. I'm going to get a lower number. So 75% of 228.4 is 171.3. That's the actual work I produce in the turbine, which means that now then I can use that to solve for the actual exit from the turbine, which is 474.4 instead of 417. So again, I could calculate temperatures and so forth, and I can see from this that it's going to actually increase the temperature somewhat. Not as significantly as I found up here, to be real honest. But that's wasted energy anyway. So, overall, what's the net effect? Well, 171.3 plus my negative 116.2 means I have 55.1 BTUs per pound mass of work net. Okay. And my heat input is H3 minus H2, but I want to use the actual value of H2. So it's 645.7 minus this 228.4, which is 400 BTUs per pound mass. The ratio of those is 13.76. So let's compare that to what we had ideally, because I have 55 BTUs per pound mass of net work. Before I had 152. Wow. 441 was my ideal with the 34% efficiency. And now then, well, let me find my slide again. Okay. Yes, it's requiring a little bit less heat transfer, but it's producing a lot less work. My efficiency is less than half of what it was originally. So process efficiencies can really, really make a difference in any process, of course, but in the Brayton cycle, it does seem to be a little bit more sensitive to that. So in our next lessons, we're going to look at how I could improve the Brayton cycle, and we're going to use regeneration, somewhat like we did with the Rankine cycle, but the physical way of doing it is going to be a little bit different. So we will be looking at that next in our class on Tuesday.